in case. Can you try again?
Weird.
I mean, there's no waiting room. Otherwise, it will pop up. Should I? Is it completely another account?
I will try again.
Otherwise, I can invite you to that.
Give me 1 second. Okay. So
yeah, now you're twice. Okay.
So we have some.
Yeah, you need to turn off the sound of one of them or the microphone of one of them.
Yeah, so the 100. Sorry, I'm so sorry. Okay, we have some issues with our internet connection and PowerPoint. So firstly, we have all this initial research that we will put together, and
just put it in thumbnails, so it's a little bit easier to see the whole thing.
Yeah.
Okay.
So regarding the agent, I don't remember if we had discussed that before.
No. I mean, this one, yes. Well, kind of.
We have to find a way to catalog, I think, all these things in a way that makes sense, like what we choose and why it's more effective, the highly structured dandelion or the less structured. So we were trying to make some tunnel tests, because maybe wind flow would be the way to evaluate that.
Yeah.
But it didn't really work as we wanted. But we keep trying.
So what are you comparing with what? Different forms
like highly. We're comparing the lattice itself.
Yeah,
like
different kind of densities and thicknesses and stuff like that.
Yeah, and also like we're comparing to how like the wind tunnel, and like if it is too structured, what happens in the floating process? Is it like
you mean too structured? You mean too dense?
Too dense.
Okay.
With the like what you see right now. For example, we try to test if it's too structured here, would it capture more humidity, more water? If you fast forward, because it's a long video.
But okay, and you say you're doing some kind of simulation tests to see which one performs
would make
better.
Sense. Yeah,
and in a kind of a better in a same environment, different geometry to a certain degree.
Yeah, here, yeah.
You say that none of them kind of gives you a different result, or some of them gives you and some of them don't?
It's like, for example, in this one, it's not too obvious how it is. Like, does it really capture more humidity?
Well, I think you need to quantify it. There's no way that you can, it's not about something that visually you're
visually, yeah.
And actually you can say, look, this has double. No, everybody will believe you.
Okay.
You can fake it. I'm not saying fake it. I'm just saying you can you can say whatever. But if you want to be consistent, it would be good that you don't fake it and you actually try to use the simulation to your benefit. So it's not the time to fake it. I'm not saying that. But you need to quantify it somehow. You need to find a way to count all those particles and say, look, this has 30% more. So it is a better way forward.
Yeah. Okay. And this, what we wanted to do in this, like we were thinking of the porosity.
But wait, before you go to the next one, what are the parameters you're testing your unit to? Like
floating and humidity retention property.
floating, you mean? Okay, no, I don't know what you mean with floating. Actually, is it like a lift? Is it like when it's a free fall? How long does it take to reach the ground? Is it? In which kind of sense you talk about floating?
I guess that it has more constraints in movement when it is highly structured compared to when it is
like stability in terms of like water loss content.
Oh, now I'm getting confused. So first one, you check how much water it can capture. So it has to do more with the surface area of it and perhaps some kind of stickiness that keeps the water particles, the vapor particles on it, right? And to a certain degree, you can actually simulate that. Now, the other thing that you're evaluating towards is, you said, floating. So what kind of simulation test do you do for that? Like literally, what do you do? Okay, so it is a free fall.
Yeah, that's a free fall.
On a specific vertical, let's say, wind blow.
But maybe we should test also how it can maneuver on that, depending on, I don't know, its structure.
I don't understand why necessarily you need, I think they're looking very cool, the simulations, but I don't know whether you need both free fall and wind flow from below, because this wind flow is a little bit unnatural for now. But what is actually a little bit worrying is the fact that actually they all touch together the ground. So there's literally no difference. And that has to do with your simulation not being completely right.
Yeah.
I think this is kind of an interesting experiment you're doing because it shows that different shapes and different geometrical configuration has totally different wind
drag
properties. So you see kind of the wind tunnel turbulence happening because of the different geometries, which is great. But perhaps you don't need to do it vertically from below. You can do also from the side or from the top, because effectively this thing, it's multi-directional, right? The wind is not coming from below, almost never. And the fact that this thing will fly is because of the lift that is getting from the side wind, like an airplane wind, right? I guess.
Yeah.
So that lower pressure in the top, higher pressure in the bottom, and pulls it up. So you need to start it more from a side perspective, I think. I don't know what is going to happen, but there's a chance it actually helps you. And then I think the free fall, it's actually weird that they actually drop the same time, because this should be, definitely the sphere should fall faster. It seems that something is not correct.
Yeah, that's why I said in the beginning that it doesn't work properly yet. And also they seem very pinned. I mean, they should be able to maneuver somehow when they respond on the wind.
Yeah, exactly. Are you doing that in Maya?
Yeah.
Did it in Maya.
It's almost like it's like simulating a leaf falling, a tree leaf.
Yeah.
There should be some kind of randomized falling pattern. Look, I think a bit more work on that. Once you start getting it a bit more variable, then it will be, I think, correct, but I think now it's obviously not working.
Mm-hmm.
It's too obvious, actually.
Yeah, we agree.
Yeah, but it's good. I think it's good as a process. It's good if you manage to do it. I think it's good.
So I think that we have this these basic attributes in our agent. So how much humidity it can capture, how it can float, how it retains it, and how it releases it, which we haven't touched yet.
Yeah.
And we were thinking that we might have to add also an aspect of the receiver, which is the receiver agent, and how this works.
The receiver, you mean after it releases it?
Yeah, like normally we have tanks, so we kind of quantify and we count how much water we have in a community or in a city by counting the depth of a tank. So I guess that we could.
But do you necessarily need that?
We don't need that.
Do you necessarily? I don't think you necessarily need it. I don't think you necessarily need to approach it so realistically. Effectively, you're building a cloud for now, right? You may end up doing something else, but you're building a cloud, and the cloud is effectively a vapor formation that moves from A to B and then releases the water in that B location, a little bit randomly to a certain degree.
Yeah, Theo was saying like we should like think how it releases collectively, for example.
Yes, but not necessarily in one spot. It's not about filling a tank.
Yeah, exactly.
Right.
So maybe there is a point of thinking how we channel this water somehow, and how, because also water has some cooling properties. It has a different heat capacity, so we could think of how we can use that in the community, since we can direct it the way that we want it.
Yeah.
And we're not like, we have not a constraint of a tank and something like that. So maybe we could start thinking of geometries and how they grow when they absorb water.
Yeah, for this one, I'm just trying to figure out if for single unit, it's like extendable, and once it's like absorb enough moisture, so or the method like for the surface tension can become a mesh network, can trap moisture, or just something.
Yeah, let's leave trap moisture because we have the agent to trap moisture. But okay, it's just as an initial study that should be more developed, but maybe we could think of this kind of expansion.
This one, just so I understand, what is the scale of this? Like, what are we looking at now?
We don't know yet, because it's very like a prototype. Very.
No. I'm saying in the way that you're thinking about it, in the way you're developing, this is a simulation of something, right? What
single unit?
Yeah. It's abstract. Yeah. Yeah, I'm saying now, like related to the receiver, not to the agent to the humidity agent. This is somehow this idea of a skin that grows when it receives humidity. We could like integrate that as a part of our design.
It's almost like the hydrogels that they get bigger.
Yeah.
Kind of, yeah.
I see. Okay.
But this could be also, maybe we should think it as a skin also, like as.
I was thinking this is kind of the skin of your dandelion. Like, if you put it in a microscope, like this, the materiality and the skin of it is something like this. But maybe I'm wrong. That's how, because That's in the presentation. That's the ordinary presentation. I thought is a kind of a zoom in, but I mean, as you say, it could be anything for now, and it's good the way you're thinking about it. You generate stuff and then you'll put it together somehow. But just it's good that you start thinking about it.
Yeah. I'm not sure whether the dandelion can expand and how this could help.
Yeah, it's not about the dandelion expanding. It's about the microcells on the surface of these little thin elements. Once the vapor goes on top of them, they may have some kind of, because they need to capture it, right? There's some kind of physics happening. Could be. I'm not saying that this is it, because obviously this is a random scenario, but there may be something happening there that it could be this zoom in of what you're explaining, but maybe not. I mean, obviously at the moment is up in the air. Okay, keep going. Mm. 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 Well, I don't know. I don't know how to comment this simulation, to be honest. I think it's a bit preliminary explaining your concept, but I don't know if it gives us more than that. And because
I think that what we should relate here, which is not still obvious, is the amount of humidity that is captured by the agent and the speed that it goes down. So there should be a relationship on how much humidity it can absorb, and like when the weight starts forcing it to go down. So we could catalog these relationship because now they go down very, very fast.
Yeah. They don't stay up there.
So it's just but for adjusting the speed and the weight that they can hold.
Okay, that's much more interesting video than the previous one, though.
Yeah, the previous was aiming to set the rule.
Yeah. I like the comment on top. Not perfect now. Okay, that's good. Keep going. Oh God, you have a lot of slides there.
Yeah, so this is like where we should introduce the force. That is this something? It's older. Yes.
I think those ones they're nice and interesting as explorations. I think you need to avoid taking it too seriously. Well, presenting them too seriously about what is going to be the behavior, because there's a lot of computation behavior here that actually doesn't happen in real life. So once you make it too much one-to-one of how this thing would work, it's actually challenging to say that, when something hits the ground, you're going to get this kind of patterning because you want this kind of a computational pattern that appears. But it's yeah, but it does it in a very specific way, which is actually quite artistic and quite nice. But at the same time, it's not really referring to the physical forces and the physical flows. I'm talking about more the previous video you showed.
But I think
yeah,
the speed that we want is more like that.
You see those patterns on the floor? It's almost like sound waves. They're a bit too fabricated in a way. All I'm saying is it's not a bad thing. It's just you need to be careful how you present it so you don't present it as that's what is happening in a physical simulation. 100% is you need to caveat it in a way that you focus on part of your project and not as a whole simulation.
Yes.
That unit gets the water, drops it down, and that's what you get. It's not like that.
I guess that what we have to get from here is the speed that the cloud can absorb the humidity. Like for me, this is nicer. Like they leave it in a specific altitude and not on the ground.
Yeah,
it makes more sense for me.
I agree. The question is, once they release it, do they go? They go up again. Okay. Well, but that's what happens here. But it makes sense, no? They release the water, they get lighter, and they go up again. Otherwise, if they release it and they touch the bottom, then something is wrong. Yeah, but all I'm saying is that they don't necessarily need to release on the ground. They may release it in the mid area, but then the unit itself is not going to continue dropping because it doesn't have any more water. It's not heavy enough. It may start floating again.
Yeah. It is able to go up.
Okay.
Yeah. And here is like we are trying to present the system. So in the beginning, we were thinking that we need something that we need to be able to, like this is the map with the world humidity data. And we need to be able to relate all these.
Where do you get that from?
It's NASA. It seems it's much harder than it looks for some reason. So we should use that as an interface, and so like which shows the roots of our cloud, like a world root map. And then we were thinking.
Are you talking about that big scale?
No,
I'm wondering whether it becomes a little bit
on areas.
Yeah. Okay.
And we firstly say that there is a system that detects the humidity. It counts the distance and the optimum path. And maybe it calculates approximately the time.
Yeah.
That it needs.
10 million agents.
Yeah.
You need to make these numbers look smaller. 9,999,999,999.
Yes, sure.
I'm just joking.
And then we've done that before. And then we calculate, like this is somehow using also topography, wind, and temperature and humidity to calculate like how the cloud will behave. So we're following the same thing for different areas, like this is in India.
Yeah.
And
I think what is critical with case scenarios, because I think you did 3 or 4 already, when you do case studies, is actually identifying the differences and identifying the behaviors. Otherwise, they are meaningless in a presentation. It's like, okay, this is Africa, this is Kenya, this is Asia, this is, and it's nothing really extracted out of that. But if you can identify some patterns or the behaviors and what is different between those regions, it would be much more beneficial. Would actually make some sense. Otherwise, it's just boring.
Yes. We have to evaluate. I mean, this is showing like how topography and wind plays a different role on how these will move.
Yeah, but identified as differences between the areas. So if you say this area is more rocky, more mountainous, then the agents are doing something else. When something is more flat, because the desert, they do, let's say, a different pattern, but there is some kind of extraction of conclusion about their behavior that you can utilize.
Yes, of course. They're not playing at all. And
okay, it's fine. Don't worry about it.
We are trying also to think
your battery is running low.
Sorry?
I thought your battery is running low. We saw a message before. Maybe that's why they don't play.
How we could introduce the more fluid behavior in this cloud. And we are trying to experiment with interactions.
They are very nice simulations, those ones. Is that still Maya?
Oh, it's Houdini.
Houdini.
It's big amount of particles.
Yeah.
Yeah, all of these are Houdini, actually.
Houdini is getting very trendy lately.
Yeah, it is. But we are trying to use data, as we did here, to control this smoke behavior, which is not very easy. We haven't found a way to do that yet. Yeah, that's all.
All right.
Should we focus more on this direction, like trying to describe different types of clouds? Or we are a bit worried because we are trying to push this direction more with the data and the cloud system, but it's not very easy to control it.
I agree. I think you need to show that you're doing it. Try to extract some conclusions out of it, but not spend too much time. You're not going to resolve it in a week or two. So showcasing it and what is your direction is a good thing, but don't overdo it, because I don't think you'll be able to get there yet. I think so far, what I would say is trying to shrink a bit the presentation, make it a bit more meaningful, a bit more dense, and kind of step by step. And I think for simulations, I think you are kind of good for now. I think you just need to extract conclusions. It's like when you did the evaluation simulations, it would be good to get some output out of that. And those ones similarly, or the previous one with a site, with the case studies, let's say, similarly extract some kind of behavioral conclusions. And I wouldn't expand much more than that, because, as I say, in 2 weeks you won't make it. But in terms of your unit itself, are you doing any progress on that?
On slide 79, maybe.
So fell down. Okay.
It's also not like for the design of the prototype, but just like maybe as a cluster, because we are thinking as maybe one cloud can has many different units, and it has behavior which can contain the moisture and deliver to other place. So just did some simulation on that.
I think you need to do more abstract stuff to start trying to capture the behavior. I don't think it's clear yet.
Yeah.
But I think that's what you're missing here. You're missing to give some visual representation or visual idea of how this thing could be. I think you're touching a bit too many stuff, and I think the jury will be like, okay, so what are they doing? Are they doing dandelions, or what is that? Is a bit. You kind of need to direct the audience towards how are you thinking about it. Sometimes abstract stuff, but positioned in the right spot in your presentation, help to visualize something, imagine something that is not there yet.
We are trying to work on this on 3 scales, so it's like 3, like the agent scale and the 2 scales of the system. So it's not 3 different stuff. It's 3 different scales. So we want them to be 3 different behaviors.
Yeah, agree. Yeah. But you need to show it like this. I think at the moment is a little bit blurry, where one scale starts and the other one finishes.
Yeah, maybe this is because of the current presentation. It's not that clear.
Yeah, could be.
Yeah. Like we have diagrams for that, and we will explain that in the beginning.
Yeah.
Theo yesterday was saying that we should show more about the cloud scale.
I agree. I think the large is generally easier because it doesn't require much detail. The medium is actually challenging for you. I think the small at the moment, I think you show enough, but it's very, very difficult to establish at the moment. I think small, what you do and what is the parameters you're thinking, and how the densities and the design of this dandelion works, I think is good. What you have, you don't need more, but I think the medium needs some work. I agree.
So if the medium, like, it needs some work, should we like try and get categories of these clouds, for example, like put down some kind of rules that differentiate from one cloud to the other?
Well, if you could, it would be good. It's effectively controlling a cloud kind of exercise, but
this is supposed to be the medium scale.
Yeah. It's actually, it's a tricky scale. It has a little bit of the small, has a little bit of the large, but effectively is what your project is about. Yeah.
I think it's difficult because it's very abstract. Like the vapor is something which is not. We don't see it, so.
Yeah.
And it's also very intricate at the same time.
I think for your project to work, it needs all three scales be presented together. But obviously, you can't do that at the moment. But
yeah, we were thinking a video.
Yeah.
Sorry?
To do this zoom in, zoom out from in a video.
Yeah.
Because they have to be connected. They have to get linked somehow.
Yeah. Yeah.
Yes.
Okay. Well, you did a lot of work from last time we met, right? Like a lot of new stuff, or at least new stuff that I haven't seen. And those ones are nice. I think those ones you need to explore them a bit more. Now we are looking at the whole thing.
Yes. And
but try to think how you can get parts of that, plug it into the medium scale. Because I think there is something interesting here to learn from.
Yeah, we could integrate that in the medium. And then we have the crystallization also that we have to explore. We had some simulations for crystallization in the mid-review.
Okay.
And so how we could use that architecturally.
But crystallization in terms of low temperature.
Yeah.
Fractal based stuff. Kind of fractal.
Yeah, so it could be like freezing this cloud in a position and start growing.
Mm.
I don't know. It's.
I would suggest you pause that for a while.
Yeah.
I think it's dangerous territory. Freezing the clouds.
Okay.
That's my feel. I think if you sort out this one, this part of your presentation, I think you are quite good. I think you just need to get a little bit more clear on the direction you're taking and on the step-by-step researching of elements and the different scales and what how you're planning to develop them and how it works together as a system. I think it's there, but not there yet. Not totally there.
Yeah, we agree.
I think it's good though. It's getting there.
This should be a video, like we should connect all this information in a video. And so the information, what we extract from each map.
Yeah.
Right?
Yeah. I think especially this one here, where, you know, how topography and humidity, they actually affect each other. And it's kind of something that you need to explore it more and you need to explain it more. And there is something there to learn from.
Okay.
I think it is a bit, I think it, you know, maybe somebody doesn't notice and say, interesting, they did good stuff. But I think this is the essence of how the system works, right? How from this 2D representation goes to effectively 4D, because you have the three-dimensionality of the topography, you have the humidity, you have time, the wind. It's so many parameters that actually they kind of get lost in this sequence of images.
Is there any other parameter that could be useful?
Well, I think you have already quite a lot. I wouldn't. What is the image on the right?
This one?
Yeah.
It's from the animation.
I see.
It's the same, just the still image, because we can't render this. It takes the video. It takes so long.
Yeah. But it's quite nice images, huh? Like even from artistic point of view, they're quite nice output.
We'll try to render the video as well. Yeah, and the intention was like to try to make it all this more fluid. I mean, if we could have a wind, have you seen these pictures, like where they saw from NASA some takes, like that they saw sand and the cloud of sand and the cloud of the cloud, how they meet each other. So if we could have these layers, like a layer of cloud and the layer
interaction of them,
and interacting like a fluid simulation, wouldn't that be interesting?
Of course. I think that's where what you're missing here, this kind of interaction of elements. I think this is what I'm kind of trying to communicate.
Yeah.
Is a little bit maps in isolation, but if you overlay them all together and their data, then it's going to start getting somewhere even more interesting.
Yes, we have to show the overlay of data in how the layers.
Exactly.
Yeah.
So all that is in Houdini. Actually, quite good. Nice.
It can. It actually works in a multi-thread way, so it is able to simulate a very big amount of data and particles.
Yeah. That's very nice.
Yeah. Okay, thank you.
Okay, great. I think you did the, it is getting there, as I said. I think it's quite good stuff.
Okay. Thank you.
Thank you. But I think what you're missing, just as it's the next step of your physical stuff, right? I mean, but I take it that you did more simulation work now, so you may need to delay the development of your prototypes. But I think it's something that slowly we need to cracking on with.
So you agree that we shouldn't push now more the agent?
I don't think you have that much time to do it. If you could, it would be good, or at least an outline of how it works. But I don't know if you can actually, because your simulations are actually quite complex. It may take a while. If you could, I think it should. But I would try to develop all the things you know how to develop for now, or you have a clear plan, rather than spending time on things that are uncertain, and then they may not output what you need for your presentation. So finish that part, and then if you have time left, you actually can change a bit your topic. Okay, I mean, yeah. If you could do it, it would be great, but let's be realistic. Sometimes it's better to stay a little bit backwards and observe where it goes, rather than try to develop fast stuff that they won't work. So maybe you should give it a bit of time.
Yeah.
I think even material experiments of trying to capture vapor and these things would be quite beneficial. Like, I think you need a bit of physical scale into your project. Like this capturing of water, like the releasing, there's some physical stuff that could happen, almost like in a scientific way. Because you are going very scientific as a project, I think you may need this rigor in the physical world as well.
Yeah.
I think
we had done some physical experiments with the fluids and things like that, but yeah, vapor is it's more difficult to depict.
Yeah. But even if you have some physical stuff, put them in.
Yeah, we should.
It's always helps. Digital and physical together helps a lot.
Yeah, it's true.
Yeah. All right.
Thank you.
Talk soon.
Yeah.
Okay, thanks.
Thank you.
Bye. Yuki, you're leaving? I see.
She can't wait. She can't wait anymore. So can we be the